Hello, we are starting the linear algebra course, and this is chapter 1, which is about linear equations and linear algebra. So the main goal or main thing in linear algebra is that we learn is how to solve a system of linear equations, and that's where we are starting. System of linear equations. So what is a linear equation and what is a system of linear equations? I believe most of you are familiar with it. So we have seen actually linear equations before, and also linear equations in more than one variable. So linear equation in one variable will be something like 2x plus 3 is equal to 5. But a linear equation in two variables will be 2x minus 3y is equal to 7. Linear equation in three variables might look like square root of 2x plus 3i times y plus z is equal to negative square root of 2i. So notice what is the difference between them is that we have here one variable, here we have two variables, here we have three variables. So this is an equation in one variable, equation in two, linear equation. Why is it linear? Because the power on the variable is 1, or even it can be less than 1. So if I have an equation x plus y equals 5, so I can think about of this as a linear equation in three variables, where my third variable is not appearing because its coefficient probably is 0. Anyhow, so what we note here is that the maximum power on the variable is going to be 1. So you can have a 0 power or a 1 power on the variable. And so that's why it's called a linear equation. And the coefficients are either real numbers or complex numbers. So now what if I want to write an equation with 5 variables? Well, what variables do I want to use? X, y, z, then what? Maybe w, maybe u, I don't know, maybe v, so on. So we don't have enough variables if we are talking about 50 variables, for example, like an equation with 50 variables or 100 variables. So that's why we have introduced a new notation for variables. So instead of taking x, y, z, we are going to take x1, x2, x3 when we have an equation of 3 variables, and then we can add on x4, x5, and so on. So an equation now in n variables then looks like something we have here, where a1, a2, and all the way to a sub n, and the number over here b on the right side, they're all the real numbers or can be complex numbers. Now a system of linear equations, or simply a linear system, is a collection of one or more linear equations involving the same variables. A solution of the system is a list. Well, we put it in this parentheses because what happens is that when we have a system of two equations, our answer could be like 1, 2. So we say this is the first variable value, this is the second variable value. If we have 3, we can have 1, 2, 5. If we have 7, we could have negative 1, 2, 0, 5, negative 1, 3, 7, 1, 2, 3, 4, 5, 6, 7, or some whatever the number is. So these are called tuples, T-U-P-L-E-S, tuples. So T-U-P-L-E-S, that is what it is, tuples. And this is a 7 tuple, this is a 3 tuple, and so on. Well, this is called a pair, and this is a 3 tuple, 4 tuple, and so on. So a solution of the system is a list of numbers that makes each equation a true statement when the values of these are substituted for the variables x1, x2, and so on. Now notice here, these are n numbers, but they make one solution for the system. there could be a situation that we have more than one solution. So in that case, we say the set of all possible solutions is called a solution set. Now, two linear systems are called equivalent if they have the same solutions. This is something we will talk about a little bit later. So let us see an example which we have done these type of problems before. So we are looking at a system of two equations and two variables. So variables are x1 and x2. So when we have these two equations, we are looking at the graphical solution. Now in two variables, it is easy to see graphically, but when we have three, it will become hard because it's hard to draw the three-dimension picture on a two-dimensional paper. And when we have more variables, it's hard to even imagine what the graph will look like. So we cannot do it with the more numbers of variables. So with two, we can easily do it. So I did it with graphing method. Okay. So you can see the blue line here is the graph of the equation shown in blue for the first example. And you see they very nicely meet at the point 3, 2, which is the solution of these two equations where these two lines meet. Now, next two lines, look at them. When we graph them, they are parallel lines. So when we have parallel lines, so they will never meet. Okay, the parallel lines never meet each other. So they just go side by side along. So then in this case, we have no solution. Then the third case is we have two lines and okay, I have this green line. What about the blue line? Well, in place of, I have here, this should have been green, but anyhow, so I can just say, let's say this is the color, purple, okay, purple. So what about the blue line? Actually, if you try to graph it, you will see that you have to graph it on top of this first line. So which means the two lines coincide, which gives us infinitely many solutions because all the points you think of which are on one line, they are also on the other line. So we have infinitely many solutions. So this example shows that when we have a system of linear equations, we have one of these situation can hold or can appear. That we have no solution, or we have exactly one solution, or we have infinitely many solutions. So as going back, now we say two systems, linear systems are called equivalent if they have the same solution set. And this will come in handy in a little while. And we say a system of linear equations is consistent if it has either one solution or infinitely many solutions. And if there is no solution, then the system is called inconsistent. Now, we will notice that we already know how to solve linear equations by substitution method or by elimination. But here we are going to introduce something we call a matrix, and we will use the matrix to solve the system of equations. So what is a matrix? It's a rectangular array, and just like numbers, like in a proper form, and then in an array or in like lines or columns put together, and then we put brackets around them. So that is what a matrix. So this is a matrix. So how did we create this matrix? If you notice here, these are three equations, and we say these are in three variables, x1, x2, and x3. Now notice here, in the second equation, we don't have the x1 variable, but because this is a system, this equation middle one is a part of the system, so we consider that the first variable here probably has a zero coefficient. So we think of it like this. So now if I pick up the coefficients of all these variables, so the first variable x1 has coefficient 1, the second has coefficient -2, and the third variable in the first equation has coefficient 1 again. So I put it 1, -2, 1 in order like that, and then I write the coefficients of the other two equations from the other two equations, the coefficients of the variables under each. So it means this one, the first column is all the coefficients of x1, the second column represents all the coefficients of x2, and the third column represents coefficients of all the x3. So this matrix is called coefficient matrix of the system of the equation. Now, what we do often when we are solving this system, we will take these numbers and put them alongside these numbers, and we call it augmented matrix. So what does the augmented matrix look like? It looks like this. So we have this one is our coefficient matrix, and then on the right we put the numbers which were on the right side of the equation, and usually we will put a straight line. So when we do the problems, we will do that. In the book they haven't done it. It becomes a little bit confusing, so for us we will put a line over here. So just to separate the coefficient matrix and the matrix we got from the column that we got from the right side. So this is called the augmented matrix. Now, since we are talking about matrix, so note here the coefficient matrix that we just saw. We saw there were 3 rows. So this has 3 rows and this has 3 columns. So we say this is of order or of size 3 by 3. Okay. So the size of this is 3 by 4. Now always we will say the number of rows first and then the number of columns. In this one augmented matrix, there are 3 rows, but there are 4 columns. So the size of this is 3 by 4, not 4 by 3. So if the size of a matrix tells us how many rows and columns it has. If m and n are positive numbers, and m by n matrix is a rectangular array of numbers with m rows and n columns. So always remember the first is the row and the second is the column number. The basic strategy that we will adopt here to solve a linear system is to replace one system with an equivalent system that is easier to solve. So we have the system of equations which we can solve by using the technique that I showed you earlier, like the elimination technique. So for example, we can eliminate this the variable x1 from the third equation by using the x1 term in the first equation, but we will keep it in the first equation because we cannot eliminate from every equation. Also, we don't want to eliminate it. We have to find its value. Okay, so but instead of doing it on the equation, we will be doing it on the matrix. But in this example, actually, we will show you how to do it with the equations and then how to put it in the matrix. But eventually, we are not going to do all this type of work with the equations. We will only do it with our matrix. So let us start. So this is an example. So it says we have to solve this system of equations, solve the given system of equations. So this is the system of equations, and we write the augmented matrix on the side here. So this is the augmented matrix. And now, as I mentioned before, this is what the process looks like. So the first thing is to have the first variable in the first row. So the first variable in the first row and probably have its coefficient equal to 1. So if there is a row and there are some operations that we can do, but not like anything that we think of. Okay? So there are 3 types of operations that we can perform on these equations and correspondingly on the matrix. So whatever we do to the equations, we will be doing to the rows of the matrix. Okay? So for example, now we want to remove or eliminate this term. So we can do is we multiply the first row by 4 and add it to the third row. So how we will do it with the matrix, I will show you later, but this is how we will write. So instead of writing it in the whole sentence like this over here, we can easily use this notation. So what we are doing is we are multiplying equation 1 by 4. So in the case of matrices, we will be multiplying the row 1. So this is row 1, denoted by R1. This is R2 and this will be R3. So we say 4R1 plus R3, and then we put an arrow and we write R3. What this means is that by doing this operation, we are getting a new R3 row. So we are changing R3 row. Other two rows will stay as they are. Nothing will change in the first or the second row. Although we are multiplying the first row by 4, but this is only to be added in here to get rid of this. First row is not changing, so it should remain the same. So with the equations, this is what it looks like, but when we are doing, we will do it like this. We can write it on our side, we can put it on a scrap paper, but not in our matrix. So our first row, when multiplied by 4, becomes this, and the third row I write just under it, and now I add. This is 0, this is giving me negative, so this was negative 2 and we multiplied by 4, so it became negative 8, and then we are adding into 5. So we get negative 3, and then 4 plus 9 is 13, and 0 minus 9 is negative 9. So our second row will become, third row is this new row. So this is the new row. The first and the second row remain the same. Okay. The next step is to now have this quantity 1. So remember, this is the coefficient of x2 over here, you can see. So now our rows, from the rows of, so note here, from the equations, we were able to write our matrix. So you should also get used to thinking about or writing equations from the matrix. So we have this matrix. So according to this matrix, our first equation will be x1 minus 2x2 plus x3 equal to 0. Because remember, there is a straight line here. Second row will be 2x2 minus 8x3 is equal to 8. And the third row will be negative 4x. So this was the original matrix. The new one is, so now the third row will be negative 3x2 plus 13x3 is equal to negative 9. So what we do now, we make the second coefficient of these in the second row, or the number in the second. So note here, this number is coming in the second row in the second column. So we want to make it a 1. So how can we do that? We will multiply the row by 1/2, or in other words, you can say we divide the row 1 by 2. So how will we write that in our matrices? We say 1 over 2 R2 gives us new R2. So what will that be? The new R2 will be 1, negative 4, and 4. So I replace this now by this new one here in the next step. So you see, so we have the new row coming in. So you can forget about this. Now this is how you will go do. Okay, the next row, process is to, now note here, we had 1 here. The thing that we did is, we already had that a 0. Now we made this quantity a 0. That's what the process looks like. So the first thing is to make the first the coefficient, or the first number in the place, first row and first column, we make it 1, and then we use that to eliminate the coefficient, the x1 terms below it, or the numbers below it. The next is to make this a 1 and then use it to eliminate the numbers below it or make it 0. So now our job is to make it 0, and to make it 0 we will use the row 2. So how can I do that? So I will multiply the row 2 by 3 and then add it to row. So R3R2 plus R3. So what will be changed? Not row 2. Remember, row 2 is just being used. So R3 is going to change. So this is going to give us new R3. So what will be the new R3? Well, if you do it in your head, or if you want, you can put it like on a side on a paper. So you have 0, 3, negative 12, and then 12. And then you are adding it in 0, negative 3, 13, negative 9. So this gives you 0, 0, 1, and this is 3. So this is giving me 0, 0, 1, 3. So third row becomes the first and the second remain the same. Okay, now from here, our next job is to make these quantities 0. Well, actually, at this stage, we can get an answer, or we can do something we call back substitution. And so this row, if you read this row, so this is telling you 0x1 plus 0x2 plus 1x3 is equal to 3. So which basically says x3 is equal to 3. So this is giving you a value for x3. If you read the second row of the matrix, the equation related to that one will be x1, 0x1, so no x1 term, x2 plus or minus 4x3 equals 4. So now we can substitute x3 as 3 and then find the x2. In the same way, the first one is the row 1 gives us x1 minus 2x2 plus x3 is equal to 0. So now we have x3, we have x2, we substitute them and we can get the x1 value. So this matrix here, where we have zeros in these places, so this is called a row echelon form. So this is called a row echelon form of a matrix. Okay, so to go further, we have to make these quantities zeros, as I mentioned earlier. Make this one is already 1, so we don't have to do anything to it. This one, but now we can use now to make the quantities in the third column 0. We can use this third row, and to make the quantity in the first row and the second column, this -2, 0, we can use the 1 in the second row. So we can go in this order, that first we use this, then we use this to make everything else 0. But if we jump to the third row first and use that to make these two quantities 0, it will reduce our amount of work. So that's what we are going to do first. To make the entries in the third column 0, the first entry and the second entry. So make the second entry 0. So making the 4 to be 0, what we do? This one. So I will multiply this row by 4. So 4R3, and I will add it to the R2. This will give me new R2. So when I multiply this by 4, 4 minus 4 is 0, and this is 12. 12 plus 4 is 16. So my new row 2 will be looking like this. Now to make this one 0, I just simply multiply the third row by -1. So I say -R3 plus R1. So which is giving me new R1, which is going to look like 1, -2, 0, minus 3. So I put it here. And now the last thing to do is to eliminate this quantity to make it 0. So to do that, we will now use the second row because we don't have a non-zero element in the third row. So we now multiply the row 2 by 2 and add it into the first row, which is going to give me new first row, and which will look like, so 0 when I multiply it by 2, it is just 0, plus 1, it's plus 1. So it's not going to disturb the quantity which we already have as 1 there. So this will become 0. Now we have a 0 here in the second row, third place or third column. So we multiply it by 2, 0, and we add in here 0. So this is not changed. So because we just made them 0, we don't want to make them back non-zero terms. So we have 1, 0, 0, and the last one, this one will be, because we have to multiply the 16 by 2 and then add in there. So what we end up getting is 16 times 2 is 32, minus 3 is 29. So that our final matrix now looks like this. So now when we read it, we can say x1 is equal to 29, x2 is equal to 16, and x3 is equal to 3. So this is our solution. And we should check by plugging it back in the equation, and if it gives us the same thing that we have on the right hand side. So you remember the original set of equations, we had 0, 8, 9 on the right hand side here, 0, 8 and negative 9, and when we plugged in here, we are getting the same values. So it means this is our solution. So what we did here is basically we did something we call elementary row operations, which we do on the matrices. So what are those row operations? These are the 3 ones. We didn't use all of them. Mostly we have used the first one in this case, in this solving this system of linear equations. But you will see that often we also need the other 2 operations. So the first is that we can replace a row by something else. So what something else? Replace one row by the sum of itself and a multiple of another row. So when I did something like negative 2r2 plus r1, so this is what I did. I added a multiple of the second row to the first row. So it made the row, what row changed? The one in which the multiple of the other row is being added. So r1 is changed, but r2 remains the same. Then we can interchange 2 rows. So we can have, first and second row interchange, or first, second, or whatever, according to our need. And the third thing we can do is multiply all entries in a row by a non-constant. So if you recall, we did use this operation when we multiplied the second row by, I think it was the second row, by 1/2 here. So we can multiply by a non-zero constant any row, but we have to do it the whole row. We cannot do it to 1 or 2 entries or 1 or 2 numbers in the matrix. Now 2 matrices are called row equivalent if there is a sequence of elementary operations, row operations, that transforms one matrix into the other. So this is, again, video is getting long, so I will stop here and do this next thing in the next video. Hoping that you understood, and we will do more examples later.